So I am very honored to be here, and thank you so much for asking us to come. This is Debby Ianson's presentation, but she can't be here, so I get to give it, which is very exciting for me. And so we've been listening to talks about how carbon dioxide is changing the climate. But of course, carbon dioxide is also changing the pH of the water and making it more acidic. And so I'm going to talk a little bit about the other CO2 problem, which is ocean acidification. And our other co-author is Paul Covert, who's here, and he made the observations, or is part of the group that made the observations in Broad Inlet. Okay. So you've already seen this picture multiple times. This is a better blow-up of it. So this is the measurement of carbon dioxide concentration at Mauna Loa, and showing that we're currently up to almost 411 ppm. The other thing I wanted you to take away from this is how fast we're actually increasing this, and we're increasing it at about 2 units, 2 ppm per year, and we'll come back to that. Okay, and if we look at time scales, I think that's really useful to look at time scales. If it's too small in the bottom, we're starting there from about 1700 and going through to current day. And we can see that, you know, from 1950, we've gone from about 300 to about 400. So we've gone 100 units in 50 years, and we're doing about 2 units per year right now. Okay. So what happens? Well, carbon dioxide dissolves into the ocean, and it doesn't just dissolve in the ocean and stay like a gas, which is what oxygen does. It actually interacts with the water and forms carbonic acid, which is that thing in the middle. And that's not very stable in the ocean, and it splits up, and most of it forms bicarbonate, which is that first one, and some of it forms carbonate. And the really important part is those H pluses. When it does that, it puts H pluses or protons in the water. And so we're increasing the number of protons in the water, and that's what we call pH. And so pH is that ratio between these protons and OH minus. And we're increasing that, and we do that simply by dissolving carbon dioxide into the water. Okay. But that's, oops, sorry, let me scroll this first. Okay, but that's not the only thing that changes the amount of carbon in the water. So you can get more carbon because we've got more carbon in the atmosphere, but also if we put organic things, organic carbon, this is picture of sewage pipes, into the water, then microbes break that down, and when they break that down, they produce more carbon dioxide. So it's not just what's happening on the surface, but it's also what's happening in the water. And we work in a very complicated coastal region with a tremendous amount of sources of carbon and a great deal of physics. So we see a great deal of variety in the amount of carbon in the water. This. Okay. So this is the what does it matter slide. And this is only part of what does it matter. Oops, that was not very helpful. It used to be very easy to show PDFs. Okay. And minus. Okay, and one more minus. Okay, and down a little bit. Okay. So this is from a study that was done by Debby and other co-authors looking at different species that live in the Pacific region and asking what is the impact of ocean acidification on those species. And you can see there's a bunch of ones that are colored red, and those we know it's going to likely be bad. There's a few there that are blue that are likely good. But the vast majority of them are gray, which means we don't have any idea. Okay, so we don't have any idea what ocean acidification is going to do to most of those species. Now this is the wild fisheries species, and Debbie's put clams on there, and then the big red circle there is gooey duck. This is not a hugely, in a global sense, the wild fishery on BC coast isn't as big as the eastern one, but economics, this is only economics, and that's only part of the story. Oh, I'm not winning here. Okay. The other thing, of course, which is much harder to quantify, and that paper didn't even try to do, is to talk about the impacts, the cultural impacts of ocean acidification. And I'm not going to talk about that here, other than to acknowledge that that is an important issue. So what I want to do now is talk a little bit more about carbon in this area. And we're going to try scrolling up. Okay, so I am going to have to, oh no, I think I can do this. Okay, so this is a very simple plot of, on the vertical axis, the y-axis is depth, okay? And the little blue thingies up there are supposed to represent the atmosphere. And what we're doing along the bottom axis is you're going to make this work for me, that would be wonderful, is salinity. And so what I'm telling you here basically is in the Strait of Georgia, the water near the surface is fresher and the water near the bottom is denser. Okay, and so that's a very classic picture of the salt. And then if I try to go down, this is a picture of the carbon in the same place, in the Strait of Georgia. Okay, so the green line is the salt, and then the blue are measurements of carbon in the ocean. And you can see that in the Strait of Georgia, just like salinity, carbon is higher in the bottom. And there's really interesting wiggles in those curves, which we can study, and they're the impact of physics and dilution and circulation. It's an interesting question, though, to ask where that deep carbon is coming from. So we will try to go down to the next slide. Okay. So let me just say why the carbon is more higher in the bottom. So those green things coming down are phytoplankton or anything else that sinks in the ocean. And as it sinks, it gets broken down by microbes and produces more carbon dioxide. So the more biological stuff that we call rain, because it kind of goes down like rain, has rained into the ocean, the higher the carbon is at the bottom. And so there's more carbon in deep water. And it turns out, for more oceanography reasons, the deep water in the Pacific is really old, has been there a long time, and so it's had an awful lot of this biological rain, and so it has lots of carbon. And so our water is naturally more acidic than the East Coast water. Okay, so now this is another vertical section. So again, on the vertical axis is depth, okay? And so we're going here all the way from 0 meters at the top, where things like plankton live, to right down at the bottom of the canyon floor where you'd have brittle stars. And then the first plot there is the amount of carbon in PCO2 units, and the next plot is the pH. And there's ranges there, and that's because we don't see one value. Depending where we go, we see many, many different values. The blue curves there are from the west coast of Vancouver Island, and then the green lines are from the Strait of Georgia. And the green lines are so big they break the axis, right? They go right over. Okay, and so there's a huge variety in different values at different times of the year from different places in the Strait of Georgia. At the surface, and then even as we go in depth, there's a great deal of variety. So let me just put that in context with the world system that we've been talking about. So those gray lines are the width of the variation we see globally in 10 years. Okay, and even if you want to make that up to 50 years, it's still, those lines are very small. So if we go out and we measure and we think about what's going on in the carbon and the pH in our local waters, everything is about the variability. We can't possibly see the signal yet in the change because it's so small compared to the natural variability. So everything is trying to, right now, just try and understand what sets this natural variability. Okay, so this is a model, because after all, I am a modeler. So we have time along the bottom. These are some recent years here, 2009 going to 2013. This is just the upper part of the water column in the central Strait of Georgia, from 0 to 40 meters, again on the vertical axis. At the top, you've got winter, summer, winter, summer, winter, summer marked. And this is contours of pH. And the blue is high pH, and the orangey colors are low pH. And so you can see here this pattern where we have low pH always at depth, but in the surface, in the summer, the pH gets much higher, and that's because the phytoplankton grow and they take up the carbon. And you can see there's a lot of variety from year to year, and that has to do with all our different weather patterns and how strong the Fraser River is flowing. And so we get a great deal of variability both in depth, in space, and in time. Okay, so this comes back to what I talked about last year, which is that both the Strait of Georgia and the Burrard Inlet are estuarine systems. So we have fresh water, surface water going out, and we have deep water coming back in. Okay, and so this is a picture for the Strait of Georgia, and that's great. Okay. And so what does that mean? Okay, so these are how we like to plot these. So remember, salinity increases with depth, and the water can go up and down, but it kind of keeps its salinity. So we plot things versus salinity. So on the bottom of every one of these is salinity, the variation of salinity, where you can also think about high salinity is deeper water. And then we're plotting here the carbon, the pH, and the oxygen of the water coming in from the Pacific. And so you can see the carbon is highest at high salinity, and the pH is lowest at high salinity, and the oxygen is lowest at high salinity. So that's what's coming in from from the ocean, and that's what's in Juan de Fuca Strait. Okay, now let's add some more data on here. Okay, so in green here and yellow is the Strait of Georgia. And you can see, which is very interesting here, is the Strait of Georgia actually has more carbon, lower pH, and lower oxygen than the open ocean. So the Strait of Georgia itself is producing extra carbon, and that's because it's a productive region. There's lots of phytoplankton growing, lots of rain coming down, lots of remineralization, and the water, microbes breaking it up, making carbon. And the water there stays for a while. The Strait of Georgia water in the deep doesn't get changed all the time. It gets changed about once a year. And so it can accumulate this carbon and become lower pH and more carbon rich in time. And then Indian Arm, Burrard Inlet, the Sail, is kind of another estuary on the side of the Strait of Georgia estuary, and it's doing the same thing. So we have fresh water coming from the various rivers into Indian Arm and Burrard Inlet. That water is flowing out on the surface, and it's being replaced by deeper water coming in from the Strait of Georgia. Okay, and it's already, that water's already enhanced in carbon because it's coming from the Strait of Georgia. And now it's coming into Indian Arm, and Indian Arm, the water stays there even longer. And so previous studies have suggested that water changes over once every 3 years. So this is just the same data as I showed previously. It's just expanded. Okay, so you can see lower salinities because we're going to go into Indian Arm, and I need to be able to do lower salinities. So, okay. And so this is the brand new data from Indian Arm and Burrard Inlet. And so the gray stars are Burrard Inlet, and the blue tealy colored stars are Indian Arm. Again, this is a function of salinity along the bottom. The black is what's coming in from the ocean. The green and the yellow are the Strait of Georgia. And so we can see that we have very low oxygen, very high carbon, and very low pH right now in the bottom of Indian arm. Okay, and again, this is because Indian arm's a reasonably productive place. We have biological productivity, and so that stuff starts to sink, and microbes break it down, and so we enhance the carbon in the bottom of Indian arm, and so we have very low pH water there naturally, low oxygen water, and high DIC water. That water renews approximately every 3 years, and so maybe at some other time we'd expect to see not such strong signals as we are now. So, in summary, the Pacific region naturally has high carbon and low pH. The Strait of Georgia and inlets like Indian Arm have distinct chemistry and can have shockingly low pH, Debbie's word. Deeper waters have generally lower pH. The surface waters have this really strong variation in time, whereas in the summer the pH tends to be high because the phytoplankton are taking up carbon. Whereas in the winter it tends to be low. And we don't know how much pH has changed in time in this region because we have very little data, and our data has really large variability. And our data, pH in the strait started being measured in this kind of way in about the 2000s. So we are talking about a very, very short time frame in what this talk is talking about. Not what you think about, but what this talk is talking about is a very short time frame, and we're just trying to understand what's going on right now, I would say. Thank you very much for your attention.